Adelante.
Ok, bueno, es un placer tener con nosotros a Alex Binks, quien va a dar el coloquio del día de hoy. Alex obtuvo su PhD en el 2015 en la Universidad de Kiel. Luego, pues, él hizo una estancia en Iria, en donde, bueno, afortunadamente compartí también habitación con él cuando estuve por allá. Luego se movió en el 2018 a la Universidad de Kiel y desde el 2021 comenzó una posición en el MIT. Alex pues, es experto en estudios de grupos con móviles jóvenes, discos de escombros, y bueno, ha hecho unos trabajos muy interesantes y precisamente el día de hoy nos estará hablando de sus últimas investigaciones. Entonces, Alex, bienvenido. You can start now.
Okay, gracias, Jesus. Okay. ¿Pueden ver? ¿Está bien?
Yes.
Ok. Muchas gracias por la invitación de hablar con ustedes hoy. No puedo creer que hayan como 4 años desde mi última visita en Ensenada. Extraño la gente, extraño el calor, pero especialmente extraño la comida. Creo que es importante que si no me entienden en inglés, a veces es porque hablo en el idioma muy británico y muy británico. So please stop me if you have any confusion during this talk. Okay, so today I'd like to talk about, well, which stellar evolutionary model possibly provides the closest match to the data that we see from clusters. But I want to start it with a quick disclaimer, which is I find the work that people put into theoretical models fantastic. It's something that I couldn't do myself. It's an unenviable task. And all I merely do is simply test these models using data. So I don't want to criticize any modelers whatsoever, but this is just a comparative study to see which models match the data best. So let's approach 2 problems with matching models with data for young stars. First of all, is that evolutionary models, which come in different flavors and different input physics, are at odds with one another and predict different ages for the same set of clusters. The second problem that I'll approach is that we're not quite sure how rotation impacts pre-main sequence evolution for young stars. We know that young stars spin up and then spin down again, but it's very difficult to find some models that match all of these physical processes that are occurring in young stars. So let's take a look at the first one to begin with. The evolutionary models are at odds with one another. Here's a simple way of demonstrating this. What I have here, the red dots represent what are probably single stars in a young cluster. Now, the solid black line is one model and the dotted black line is another. I'll say that one of these uses standard input physics, known as the standard models, and another one accounts for magnetism on the surface of the stars. Now, as you can see, there's a factor of 2 difference between those 2 models. So 100% difference between 2 models trying to predict the same cluster. Now, this is amplified by the fact that during this epoch, around 10 to 20 million years, there's a lot of changes going on during the pre-main sequence. And this really is the period where, you know, stars are evolving, disks are starting to be dispersed, you get planetary formation on this timescale. So it's very important that we get these ages right before we can fill in our picture of evolution at young ages. I should say in this talk, by young, I kind of mean anything that's younger than around 100 million years. So around that time scale. Okay, so here's an example of why this could be important. What you see here is the rather famous AU microscopii, which is in the Beta Pictoris moving group. And what's special about AU Mic is it's a young star. It has a debris disk around it, and it's a debris disk around a very low mass star of spectral type M. And just recently, a couple of years ago, a team looked in the test data and realized, well, there's also a planet here. So to get the age of the planet right, we need to get the age of the star right, of course. But it's not just that. Also, the models predict different masses on the order of 30% discrepancies and radius discrepancies of the order of 20%. There's similar examples, of course, in other nearby moving groups. For example, another one here that was found with test data in the Tucana Horologium Association, and a rather famous example in the Columba moving group with a 4-planet system. So we really need to constrain the ages of these if we want a better picture of the formation and evolutionary scenario of planets and stars themselves. I'm focusing on young nearby examples here because obviously you get much higher resolution, you can do direct imaging, and it really gives us a window into how these systems evolve. So another topic of, rationale for why ages are important is now that we have this whole swathe of Gaia data, we've, in the astronomy community, found lots and lots of different structures in the nearby Milky Way. Sort of things that are like long strings of clusters. And just recently, a structure was found which was dubbed the Radcliff Wave. Now, the idea of this is it was a bunch of star-forming regions that was originally thought to form what was called the Gold Belt, which is a partial ring of stars. But now we have Gaia data to much higher precision. It appears that this thing looks like a kind of sinusoidal structure which extends through the local arm of the Milky Way. And it's giving rise to a whole new area of stellar astrophysics with these strange entities. So it's dubbed the Radcliff Wave. That's for the Radcliffe Institute, not because of the guy that played Harry Potter a few years ago, of course. Okay, yeah, so I mentioned about the large streams of stars, a couple of 100 parsecs in length. Yeah, we need to study the ages of these, get the ages right, to get a better idea of the star formation and stellar evolution on a kind of galactic scale. If we can trace back the orbits of these with Gaia, and we know their ages, then we might be able to test what might have formed these large extended structures of young stars that we see. Effectively, it's called galactic ecology. And just recently, we can get a window into this. I'm going to go over this very quickly because I know next to nothing about how to create a standard stellar model. But effectively, what the models do is they solve for the structure equations. And a standard model would try and solve these 4 equations you see in front of you. And they need to connect the stellar interior to the stellar atmospheres. What they don't do is have any additional form of physics in the form of things like magnetic fields or accretion, which is why they're called standard. So obviously what's found from these models is luminosity and temperature for a given mass and age, as well as composition. But let's just take the Hertzsprung-Russell diagram as the first example. Once we've gone from the Hertzsprung-Russell diagram to compare this with data, we need to make the right photometric transformations, account for any kind of reddening or extinction from various regions of the sky. to compare it on the observational plane, which is the colour magnitude diagram. So I mentioned a little bit about magnetism just then, and there's lots of empirical evidence to show that young low mass stars are much more magnetically active than their older main sequence counterparts. This can be manifested in lots of different ways. For example, you've got H-alpha luminosities, X-rays, which probe the coronae. You can have direct measurements of magnetic fields through Zeeman Doppler imaging. And using mid-infrared observations, one can actually probe the structure of star spots themselves. And all this evidence points to, well, that young stars tend to be more magnetically active. The net cause of larger amounts of magnetism is that the magnetic field that's created on the surface of the star traps the flux, the heat that's coming from the center. So effectively, it inhibits convective transport near the surface of the star. And this causes radius inflation because, well, the luminosity remains the same, the energy has to escape somehow. So it does so by inflating and making the surface larger. So we can get this in the form of star spots or in the form of large-scale magnetic fields. The idea is whatever is causing this is causing an inflation of these young stars. The net effect of that is that these stars are brighter, the radius is larger, that cools down the core of the star for a given mass and age. So it slows down the evolutionary process as the stars are evolving onto the main sequence. Okay, so before I go into our work on it, let's have a look at how rotation plays a role in evolution. So it's been known for some time through models and through collecting rotation periods for low mass stars, that stars are kind of born perhaps locked to their disks. They then lose their disks by a process of angular momentum conservation. They spin up, they go to a higher rotation rate, and eventually lose that angular momentum through the form of stellar winds until they become slow rotators, similar to what we see in the sun. This has been found empirically, mainly through a process called gyrochronology. What gyrochronology does is it compares rotation periods with the effective temperature or the stellar colour. And what you can see through age, if you like, through different age clusters, is a kind of transition to the fast and slow rotation at a given spectral type. So this has been like a useful probe for stellar ages, which I'll get into later on. So let's have a look at how rotation affects the brightness of the star. The idea here is that fast rotators are generally brighter than the slower ones at a given effective temperature. The idea is that they generate more magnetic activity. This causes more inflation, so they're brighter and redder. And there's lots of evidence for this in clusters where we see this difference in absolute magnitude, if you like. What we see is that the slower rotators tend to be fainter. So there's lots of evidence for that. And the one that I'm particularly interested in is how rotation affects the amount of lithium that is observed, or how much lithium has been depleted from the initial supply that a star has. And it's been known for about 30 or 40 years that amongst K-type stars, so these are stars that are around half a solar mass to 1 solar mass, that the rapid rotators are less depleted. They seem to hold on to the lithium longer than slow rotators. And there's a similar kind of perhaps rationale for this, which is that this inflation slows down the pre-main sequence evolution, cools the core of the star, so the temperatures required to ignite lithium get reduced in the core of the star, which causes less convective mixing. So there's plenty of evidence for this in young clusters as well. I should point out that this has only been seen in K-type stars, really. Not so much for M-type stars. This is probably due to observational limits in the past and the fact that M-type stars are more likely to be fully convective, so perhaps they haven't been studied in much detail. So at this point, we should ask, how do we compare the models? And of course, the only real useful way of comparing theoretical models is to test them with observational data. And the tool we have at hand, of course, is star clusters. So let me introduce you to the Gaia ESO survey. And the Gaia ESO survey was roughly a 5-year project between 2011 and 2016, which obtained just over 300 nights on the Very Large Telescope. And it observed over 100,000 stars spectroscopically, around half of which were candidates to known star clusters. Some of them, within the nearest 1 kiloparsec of the sun. The usefulness of using the same survey to test the data, to test the models, sorry, is that the data is homogeneous. It was all observed using the same methodology, so it's less prone to systematic effects in the measurement. So what we've done is we've picked 5 clusters aged from very young, around 5 million years, like N2264, all the way up to something where the kind of N stars are approaching the main sequence, which is around 125 million years. And we want to see how the objects in these clusters basically evolve, how they progress through age. Now, we picked very high probability members of these clusters. And the way this was done was through a kinematic selection. So we have Gaia, which provides the on-the-sky velocities, the tangential velocities. The Gaia ESO survey, we get radial velocity from the spectroscopy. So we can actually probe the 3D kinematics of the clusters and pick the ones that are co-moving in 3D. So then the trick is, from those members, find the best fitting isochrone on a color magnitude diagram. And whatever the age is that provides that best fit isochrone, have a look to see, does it provide a reasonable fit to the lithium equivalent width versus color diagram? So we're kind of probing 2 different facets of stellar evolution. You've got the kind of change in brightness as a function of color, and then you've got the change in lithium abundance as a function in color. And if a model was truly correct, then it should be able to predict both of these simultaneously. So we're also testing rotation periods. So I just want to quickly draw some attention to some of the work we've been doing with TESS. So as you probably know, TESS is this large NASA satellite mission, which is mapping the skies photometrically. And it's doing it in various modes. One mode is a kind of 2-minute high priority sample of stars, which have lots of exoplanet candidates around them, and they're very interesting. But there is also an extra set of data, which is a all-sky survey, which takes 30-minute cadence observations. So each of these test seasons is 27 days long. And I think it's now into its 4th year now, TESS. It's been going for some time. So all the clusters in this work, those 5 clusters that we selected, have all been visited at least twice by TESS. So this can give us hundreds of new rotation periods, simply just by downloading the test data and doing a periodogram analysis. So we extract the light curves, we run the periodogram, and we run some tests for the reliability of those rotation periods as well. That's great in theory. Of course, we've got some open clusters that are quite crowded, particularly in things like N2264. The stellar density is quite often, you tend to get perhaps 2 or 3 stars within a couple of test pixels, so it can suffer from contamination. And at the faint end, we perhaps get low amplitudes from tests as well, particularly around V = 16 or 17. But the plus side is we've got lots of new rotation periods. First time ever for Lambda Ori or for Gamma Vel. And we can use the rotation period data set to compare it with things like the color magnitude diagram, the lithium depletion, or just gyrochronology itself. And you can see just this short video showing you the kind of range in, well, it's like a gallery of some brilliant light curves and some not so brilliant light curves. So we're going to have to sort of channel and filter out the good data from the not so good data and test the reliabilities. I'm only going to go through these quickly just for time. But essentially what we're doing is seeing how sharp is the periodogram signal. Is the power you get from the periodogram much greater than, say, the second highest peak, or compared to, say, the false alarm probability level? So we've got some factors to take care of with that. Also, we can sort of collect from Gaia all the stars that are within, say, 4 or 5 pixels from the centroid of the aperture where we're taking the photometry. And we can add these into the light curve just to see how much flux we might expect from the background compared to the stellar source itself. In 3 of these clusters, some observations have been made already, and we've seen around an 80% agreement with our TESS rotation periods compared to what we see in the literature. It's not perfect. We find that there's a lot of short rotators that could be fast rotators that could be slow rotators, and vice versa. And of course, with TESS's limit of 27-day seasons, once we get to around 10 days, we do start to see a few issues with the reliability of the very slow rotators. But I can come on to this later if we want to discuss kind of ways that we've channeled and filtered the rotation periods. The plot you see on the right is just the kind of gyrochronology, if you like, the rotation period versus color for the 5 clusters in question. And you can see from the youngest clusters, sort of K and M, the K-type stars, so things with G minus K of, say, 3 or less. You start off with a range of about 0 to 10 days. Things tend to then spin up by the age of something like Gamma Vel, and then they tend to spin down once again by the time you get to these sort of 100 million year old clusters. So at least it's showing to first approximation what you might expect from gyrochronology. Okay, so let's test some of the evolutionary models. Can they match the color magnitude diagram and the lithium dispersions? Just very quickly then, what we do, we correct for the distance modulus and the reddening, just using single values predicted for the clusters, using the Gaia ESO data itself. This comes from a paper that Richard Jackson wrote, well, just at the start of this year. So we're taking the values from that. So once we correct for the reddening and the extinction, we separate the probable single stars from the probable unresolved binaries just by fitting a simple low order polynomial fit on the CMD, and then picking the faintest 50% of the cluster members. So this basically gives us what is the single sequence, which we use to fit the models. And it's a fairly simple procedure. You know, we just loop the isochrone over and over in terms of ages in steps of 0.1 million years, calculate the reduced chi-squared values, find where this is a minimum, and then we can get statistical error bars from that, and also systematic error bars from the uncertainty in reddening and distance modulus as well. We find the systematic errors are generally larger than the statistical errors. That's probably just because we've got several hundreds of stars each time that we're observing. Yeah, so that's how we do the fitting procedure. Just a quick note on these magnetic models. I'm going to be comparing one flavor, which is kind of a standard model, which doesn't use any additional input physics. That's kind of like a baseline model, if you like. And then I'm going to use a family of magnetic models. So by magnetic, I have two different models. The first one is a sort of equipartition magnetic field, which has a fixed value. The field strength has a fixed value of 2,500 Gauss, which is sort of a typical value for what you see in young K-stars. The second one, oh, I should say that that's fixed, so we can't actually change the value of the magnetic field strength in the first model. In the second set of models, this accounts for inhibition of flux using cool star spots. And there's two parameters that can change here. The first one is the fraction of the flux that's blocked by the cool spots. So we can alter this. We have done from 1/10 to 3/10 of, the stellar flux. This has the net effect of moving the isochrones upwards, so to speak, on a color magnitude diagram. So if you look at the plot on the right, all these solid lines move upwards if you increase the amount of flux that's blocked. The second parameter you can change is the temperature ratio between the spots and the photosphere. So these are generally between 70 to 90%. So, so that's a level of going from 70% of the temperature. Well, it's a temperature ratio, sorry. So the net effect of that is it moves the isochrones redward. It doesn't block any flux, so things don't get brighter or fainter. They just move redward in color, the closer you get to a value of 1 for that ratio. And the kind of flux equals 0 acts as a standard model as well. This is just basically saying 0 spots. Okay, so let's have a look at some of the fits to these clusters. The first one is NGC 2264. Has a kind of literature age of around 5 million years. Now, I'll just take some time to try and map out what you see in front of you here. So the top two plots are the standard models. The bottom two plots are the magnetic models. And yeah, the plots on the left, this is the color magnitude diagram. And on the right is the lithium versus color plot. By lithium, I mean the amount of equivalent width that you measure in the star. Red symbols indicate the likely single stars that are being fit. Blue stars are the ones that are excluded from the fit because we suspect they're unresolved binaries. Finally, the objects that are denoted by squares, we suspect are highly accreting objects. We got this because we can measure the H alpha from some of the Gaia-ESO data. So those aren't considered when we compare the lithium plots later on. I'll explain in more detail later. So for the first cluster, we see that the standard models, the ones on the top, almost entirely agree with each other. They overlap. This is 3 different models, all from different authors, and they all pretty much agree to within, say, 1 million years. The magnetic models, they vary depending on the amount of magnetic field strength, and that's perhaps not so surprising. So the more magnetically active the model is. So in this case, we're saying that the value of beta, the amount of flux that's blocked at the surface, the higher that value is, the older the ages are that are predicted. Perhaps we can't get much from these plots because this cluster is so young that you can do a fit to the color magnitude diagram, and we can discuss how well they fit, but there's hardly any lithium depletion in the young stars. This is simply because the cores of these stars haven't got hot enough yet to ignite lithium. So what you're seeing is a kind of scatter around the initial supply. So
Alex, what is the units of the equivalent width?
Oh, sorry. Yeah, it's milliangstroms. Sorry, yeah, I forgot to put that on. So yeah, these values. Yeah, no problem. Okay, so the second oldest cluster in this sequence, Lambda Auri, we're starting to get slightly older ages by a couple of million years. And we see the kind of same differences, if you like. First of all, between the standard and magnetic models. The magnetic models are systematically older. But again, it's hard to break the degeneracy with color magnitude diagrams, with lithium diagrams, simply because we're still not at the age where lithium has started to burn in any of these stars. So the next plot is the one that I find the most interesting cluster because there's so much physics going on in this cluster. There's so many evolutionary processes. And this is for gamma Vel. Now we start to see some real differences between the standard models and magnetic models. Because it's one thing to say that they are different, but it's another thing to say which ones work best. So as you can see, the standard models do a reasonable job of fitting the color magnitude diagram. Probably still a bit too bright at high masses and a bit too faint at low masses. The shape of the magnetic models are better, I would say, overall for the color magnitude diagram. But when we go to the lithium plot now, we see that the models predict absolutely no lithium depletion in the standard models. And we're starting to see some depletion predicted for gamma Vel, but nowhere near enough to cover this kind of mid M-dwarf sequence where you've got a range from 0 to 600 milliangstroms, which is effectively fully depleted to not depleted at all. We've got two of the older clusters, but for the purpose of time, all I'm going to comment on this is that it's as these stars approach the main sequence, the power you get in getting the right ages decreases because there's more stars that are approaching the main sequence. So these uncertainties get much larger in the systematics. And you can see that there's a large spread predicted in the lithium as well. So that's for those ones. So just very quickly, what have we learned from that? The standard models all agree with each other. Probably unsurprising given that they use similar input physics. The CMD slopes, if you like, the curvature of them, don't quite fit the observations, and they don't capture any lithium depletion where lithium depletion is initiated in the low mass stars, like in gamma Vel. On the contrary, magnetic models provide perhaps better shapes at young ages. They're highly age sensitive, and by that I mean the more magnetism you put in them, the older the ages are that are predicted. And they're generally about 1.5 to 2 times older than the standard model predictions. But there's a fly in the ointment, which is that the magnetic activity that goes into the model and the age are degenerate in the fits. So you could have an old, highly magnetically active model, or you could have a young model with no magnetic activity at all. So there's degeneracy. And perhaps we're seeing this with gamma Vel. You could ask yourself, with all these fully depleted and non-depleted objects in this weird spread here in gamma Vel, is that indicative of an age spread? It turns out that the faintest stars within this box, where there's the largest lithium spread, tend to have the least amount of lithium. So there's clues that there might be an age spread there. And one way to test this would be to fix the amount of magnetism in one of the spots models. So here you can see I'm fitting a value of 30% flux blockage and 90% for the temperature ratio, and changing the ages in steps of 5 million years. They don't give perfect fits to the colour magnitude diagram, but they're perhaps within systematic error bars. When you compare that with the lithium plot, you can see quite nicely that they actually carve out the edges of that lithium dispersion. So that's a contender to say that, you know, the lithium might show that there's a large age spread in gamma vel, perhaps even of the order of 10 to 15 million years. Another way of looking at this is you fix the age and you change the magnetic activity. You can get some reasonable fits, not quite as good as changing the age, but to within a certain threshold. You could also change the spot details. If I was to bet which one, it feels like actually an age spread covers the data range a little bit better, but the magnetic activity spreads can't be taken off the table as well. So the same thing seen in the older clusters, but I won't go into that just for time reason. Let's just go back then now to how rotation plays a role, both in the colour magnitude diagram position and in the amount of lithium, how much lithium depletion has taken place within the stars. So what I'm going to do, I'm going to compare the 5 different clusters, and I'm going to split them into bins of K stars, and they're going to be subdivided as well. And then I'm going to have a look at the M stars, just to see if there's any trends with rotation and CMD position, but then also with the lithium. So let's start with the CMD. So we're going to see basically a fairly complicated grid of objects here. I'll try and talk it through nice and easily. The y-axis, here you can see it's split into 3 different groups. You've got all the K stars, the early K stars, and the late K stars. The more negative a value is, the fainter the star is. By faint, I mean compared to the typical sequence, the sequence that was used to split the unresolved binaries and likely single stars. And then going along the x-axis, you've got longer rotation periods, and you've got the 5 different clusters. So let's just have a look visually if you can see any trends. And the answer is probably not for the young clusters. What you can see perhaps is in the slightly older clusters like N2547, you see a trend where the fainter stars are slower rotators, or brighter stars are faster rotators, and perhaps the same thing in N2516, but not really anything conclusive to write home about. And I must say as well, perhaps not so much as well with the M stars. Some of these suffer from low number statistics, so you could argue there's something going on in Gamma, but there's only 7 stars in this bin, so perhaps nothing too conclusive about how rotation affects brightness or position on the colour magnitude diagram. How about rotation versus lithium depletion? What we're looking for here with some of these clusters is, do we replicate the lithium rotation connection that's already been seen in the clusters? And the answer is yes, for some of them, perhaps these ones. So here we've got N2547, 35 million year old cluster, and we can clearly see that the brightest stars are the fastest rotators. So this kind of adds to the collection and adds to the sort of like combined understanding of the lithium rotation connection. We see it at around 35 million years. And we also see it statistically. There's actually a very low p-value and quite a significant, correlation here. It's just that there's a lot of objects that are slow rotators in clusters that are kind of Pleiades age, like N2516. So I'd say that we replicate what you see in the kind of lithium rotation paradigm for K-type stars. What about the M-type stars? This hasn't really been studied in that much detail. The answer is, well, we see hints perhaps of a lithium rotation connection at very young ages, which is surprising because we didn't expect lithium to have undergone any depletion. And yet it looks like amongst the very fast rotators in the early M stars, there may be a lithium rotation connection. We might even see something very strange in Gamma Vel, where the trend is reversed, where actually it might be that the slower rotators are the ones that have more lithium. So that kind of goes against the idea of what's going on in the K stars. Again, I should say that these are low number statistics, and perhaps a better way of commentating on the trend in Gamma Vel for these sort of like mid-M stars is that we don't see any trends at all, which might itself be interesting because lithium depletion has certainly kicked in for those kind of stars in Gamma Vel, as you saw before. So hint of a reverse trend, definitely compatible with no trend, but definitely doesn't replicate the lithium rotation connection like you do for the K stars. So I'm just going to end to suggest what might cause that lithium rotation connection. And there are kind of two ideas on the table. The first one is one that we hit on before, which is that this rotation connection is correlated with magnetic activity. So as we've seen before, more magnetically active stars, so the fast rotators, they tend to be spottier. They slow down the convective mixing, they inhibit it, it inflates a star, it cools down the cores of the stars themselves, it makes them brighter, redder, and as a result, less lithium depleted if they're fast rotating. And as we've mentioned, it's seen before in lots of clusters. So there's lots of ticks for that. However, for that to have been set up correctly, those stars would also have been the fully convective N-type stars at much younger ages, where the levels of magnetic activity are generally saturated. And we definitely see that through kind of chromospheric activity and to some level star spots as well. But crucially, this happens around the same time as the ignition of lithium burning in the fully convective stars. So it's hard to understand why then would you get a kind of connection between magnetic activity, or another way of saying that is fast rotation, and lithium. Why is there a trend rather than a kind of just random scatter around zero? Because those stars would have had to have been fully convective. So there's a problem with that idea. Another idea on the table is that mixing processes within the cores of the star, within the convective zones internally, cause more depletion, more convective mixing from differential rotation. And that sort of halts the convective overshoot from the sort of inner radiative region of the star. And it might explain what's going on again for the older K stars. Except you sort of arrive at the same problem where, those M stars still would have had to have been fully convective. They certainly weren't born with radiative cores. They are developed after tens of millions of years. So again, we land at the same problem where we can't really account for the trends. So unfortunately, more questions than answers at the end of this talk. We can also say that neither scenario can account for those M stars we saw in Gamma Vel. So it's possible that there is a large age spread that we're observing in Gamma Vel, which would be much larger than what's typically quoted for young clusters. I should say that if that also occurs in N2547 and older, it becomes less significant as stars approach the main sequence. It's like as if, you know, they erase memory of that evolutionary process. So 10 million years is a small factor for older clusters. But it's interesting to see what's going on in Gamma Vel. Just recently, another idea that was put forward is that rotation changes the conditions for convective stability. So, you know, if the Schwarzschild criterion is changed in some kind of way, that would affect the structure of the star. You know, so there might be some leeway into that, but yet we still have this problem of fully convective stars. Perhaps convection isn't quite properly modeled, and we need to have a reassessment of that to see how it changes the structure internally of stars and what we see on the photospheres as well. And yeah, that's the scenario where we're at. So, you know, I don't even have a conclusion page. We've just released a paper. It should be being released by MUMRAS in the next month. It's on archive as well. So yeah, what we're taking home from this is that the models obviously disagree with one another depending on whether you have magnetic models. The more magnetism you have in the star, the older the fits are to the colour magnitude diagram, and they go some way to replicating the observed lithium dispersion in young clusters. There's lots of unanswered questions about the lithium rotation connection and, you know, what's causing that extra convective mixing within the M-type stars, why we even see a lithium rotation connection at all. And there's lots of work to be done in the future. Perhaps we need to get more direct observations of star spots themselves. That would be useful. So I know that a lot of clusters have been observed with things like apogee. And if we could get mid-infrared observations and really probe the star spots one by one, we could perhaps use models that way. Or an even more expensive way would be to actually do Doppler imaging of these stars and actually map the magnetic fields. But that's some way into the future. So at the moment, this is as far as I think we can go with testing the models, unless we can break the degeneracy with more magnetic field measurements. Great, yeah, so I'll just leave it there, and yeah, feel free to answer any questions. Gracias.
Gracias, Alex. Thanks. Questions? Well, I have one. This H-spread possibility in Gamma Vel, you can test if using radial velocity and proper motion, if there is different kinematic structures in the same field of view. Have you tested this possibility?
I'm glad you asked, Jesus, actually, because I should have mentioned that when I was describing Gamma Vel. So part of the Gaia-ESO survey, one of the papers that came out from it, is that there are two distinct populations in Gamma Vel, which they know as population A and population B. They're separated by about 40 parsecs in distance, and I believe about 3 kilometers a second in radial velocity. Not so much, but enough for the measurements to spot two distinct Gaussian shapes, if you like, in the radial velocity profiles. So these ones have been specifically filtered to be population A.
Okay.
So we do think we have a single kinematic population, yeah.
Excellent. Julio?
Hi, Alex.
Hi, Julio.
Very nice talk. Thank you. I am happily surprised about this inflation that you mentioned connected to the size of the stellar spot. No, given that you have to free out the energy otherwise, then you have to inflate the star. And I was wondering, in a big scale, I mean, compared to the size of the star, how big this spot has to be in order to consider in the model evolution the inflation that this affect also. So
Yeah.
typical, I mean, it's interesting how the size of the spot that you have to include in order, or the area, maybe it's several spots, of course, no, but I mean, talking about how much fraction of the star or the area you're thinking.
Exactly. I mean, of course, that depends on, what should I say? That depends on the temperature ratio of the spots as well, to figure out how much flux is being blocked.
Yeah, how much is this? Like 2000 Kelvin, no? 1000?
It's so. What I can say is that for no one knows.
Yeah, nobody. It depends on the star, on the type of the star.
Yeah. So what we can do is measure the fraction of the surface of the star that's covered by spots. It's a lot harder to get the temperature ratios. Yeah. What I can say is that, say if you pick 80% temperature ratio, then if you then said 30% of the flux was blocked, that's around 50% of the star is covered by spots. And from observations done by Apogee of like N-type stars that are quite active, that's not an extreme value. And we kind of see in things like the Pleiades, you know, you can get spot coverage of about 60, 70% quite easily.
Okay, yeah, it's an important amount, half of the area. It's really big, which is really magnetic and strong fields. Thank you. It was very nice talk.
Oh, that's okay. Thanks, Julio.
Okay, Carlos.
Hi. Okay. Great talk. Very entertaining.
Thanks,
also. Because you very visually was very entertaining. I have a question, Alex. So we are dealing with these problems of trying to characterize how do we define ages for pre-main sequence stars. But I wonder what about the model atmospheres themselves, right? So we can do our best to try to fit evolutionary models to the resultant feeds that we do for temperatures, gravities, and other parameters of the stars. Yes. But we are also dealing with model atmospheres that also still don't have all these parameters fully considered, or we have lots and different versions of the same thing for the same set of parameters. So I wonder if you can comment on this.
I can try to, which is what we decided to do was use the Baraf 2015 models for the conversion from luminosity to the color magnitude diagram. And we're in communication with Isabel quite a lot about making that conversion as well as we could. And the reason we settled on the Baraf conversion is because they couple the atmospheres to the stellar interiors in a kind of very consistent way. And, I was advised by lots of stellar modelers that would be a reasonable way forward. So then what you do is you have like a kind of fit between luminosity and temperature, and then you do kind of bolometric corrections from the Baraf isochrones. So every time you have a luminosity from a different model, you make the Baraf correction and map it on that way.
Okay.
At the very least, if it's wrong, it's consistently wrong. So all the models are using the same scale.
Right.
Yeah.
Thank you.
Oh, no problem. That's okay.
Okay. Rafael?
Thank you, Alex. It was very nice talk. And though I have more doubts now than before, which is good.
I know, me too.
Which is good.
Yeah.
Let me turn this on. I was thinking that especially in the late case and early M stars, in the younger clusters, they should be variable. And then what do you use as the magnitude, and what do you use as for the color? I guess the variability is usually like FLIR style. So you could use the minimum. I don't know about the color. I have no idea. What do you, would you comment on this? And I have a second favor to ask you for you. That is,
sure.
could you tell me what would be a nice reference for the lithium abundance as measured from the equivalent width? Okay,
Sure.
in this kind of stars.
Okay, yeah, of course. So, can I answer the second one first and the first one second?
Go ahead.
Okay. So
the
lithium measurements, they initially came from the Guy-Riso survey. They have their own in-house conversion, and they measure equivalent widths in a kind of fairly systematic way. However, when we looked at the data, what we actually saw is some strange offsets in the N-type stars. So imagine you've got something like N2516, that's the age of the Pleiades. You want to see a scatter of something around 0. You wouldn't expect an offset of like 100 or 150 milliangstroms. So that prompted, one of my colleagues at Keele, Richard Jackson, he made a piece of code, which effectively what it does, it takes all the M stars that are around that field of view from the Guy-Riso data, and it fits a background. So it's like an empirical fit to the continuum, if you like. So then you have all the stars that have no lithium whatsoever, and you can use that to then measure it against your data set. So it became quite a fiddly job to do, as you can imagine.
Yes.
No, I can't speak on behalf of Richard, but I'm sure he's a really nice guy. And if you ever wanted to get in touch with him about measuring equivalent widths in that kind of empirical way, then I'm sure he'd be happy to.
Thank you.
What was the first one? I'm sorry.
About the magnitude and color of the stars, they are supposedly variable. Many or most of those stars. So, have you an idea what do they do?
I mean, it's true, and it's something to be concerned about, because they can range sort of like 0.2, 0.3 of the magnitude. They can scatter around. We just have to hope at the moment that we have enough stars within a given color that it actually probes active and inactive stars at different parts of the sort of activity cycle, if you like. Ideally, we could. One thing I was thinking about was, can you get 2 different clusters and merge them into the same age group? But that probably comes with its own set of problems. So for now, yeah, the answer is we didn't really do anything for that. We just kind of hoped that there were enough stars that would average out.
Yes, of course, this variability is usually like a FLIR when it's important, besides the variability due to the spots, of course. When the other variability is like a FLIR kind, and it's it's FLIR.
Yeah.
If you have several measurements, then you most probably have a reasonable measure if you use the minimum or around the minimum.
One thing we did do.
Okay.
One thing we did do, Raphael, is we did it in 2 different color magnitude diagrams. So we kind of have like optical versus near infrared. And then we've got like optical versus optical as well. You know,
Okay.
like a kind of Gaia CMD.
Yeah.
Still might be there though as a flare. That's true.
Thank you a lot, Alex. Thank you.
No problem.
Jelaine.
Thanks, Alex, for your talk. It was very interesting.
Thanks, Elaine.
Question, and I would like to know if you can like elaborate on something you said when you were showing like the effects of spots and then the effects of magnetic fields. You said the spots fit better. But to like that was not super clear to me, and I would like to know like a little bit more about what you think. So if we consider like exactly the same age, then the spots fit better. But then can you just like put up? I don't remember what
Okay. I'm just thinking that
slide you showed, but you showed like the lithium depletion on one side for the two scenarios, and then on the other the main sequence.
That's right. Yeah. So when I say they fit better on the color magnitude diagram, what we tend to see is the non-magnetic models, they're too faint for the very low mass stars. They can, especially at young ages, they seem to be about half a magnitude too faint. And then when you go to the kind of higher mass early K-type stars, they seem to be like a couple of tenths of a magnitude too bright. And I think what happens with the spot correction is that the stars on the faint end, they sort of, the models would predict something brighter because the actual change in effective temperature isn't so much, but you have a radius increase. But then the correction at the higher mass end sort of corrects it in the other direction.
Can you like
So
show this graph while we talk about it?
Yeah, it might be a bit tricky to do.
Okay, if it's difficult, don't worry. I mean,
Oh,
I
no,
remember. Okay, I remember. But I want to see. Like, I understand now what you say in the sense that the effect of the spots behaves differently for the low mass and high mass versus the magnetic fields, which seems that is like more like.
Yeah, so
it has,
the
like,
gamma
different-
vels, kind of an example there, where if you look at the standard model, they're just predicting things that are a bit too bright at the sort of early K-type stars. And then as you go down the sequence to more like N5 and, you know, much lower masses, they tail off. If I've cut the plot off here, but if you could continue, this thing like really goes down at this point. And then if you look at the kind of magnetic ones, they just seem to go through the sequence a lot better.
So, okay, so I have another question. We know that these young clusters have an age spread of a few, you know, like the age spreads that you showed as a test was like from 0 to 25 million years old, but you don't consider like an age spread in these young clusters of like 5 million years old. You know, like would the effect then, could it be that there is an age spread and there is like magnetic models or something like this?
Oh yeah, I mean, if you look
a
at
combination of all the things you separated them very clearly in your talk, like spots and magnetic fields, but actually they're related and both of them can be affecting the
exactly.
I don't know if you've like thought about it or how you would go to like bring them together in this scenario that would be like more complete in the sense that the magnetic fields cause the spots.
I'm almost certain that there's a significant age spread in the clusters younger than gamma vel. You can just see that from this like really large spread, even in the things that we've defined as single stars. Now, it's not necessarily that we've captured all the single stars there as well. Many of the blue objects might turn out to be that as well. It's only that because there's no lithium depletion that occurs, it's very hard to probe that any further. So I agree that you could make a model at 10 million years and 2 million years and kind of envelop the red objects there. No, the only reason I didn't do that is just because I saw Gamma Bell and I got overexcited and saw all this lithium depletion, and I thought that's the one I want to focus on, because that's where you start to see like the real changes happen with the lithium. But it's a very confusing picture to put it all together, I have to say.
Of course.
Yeah.
Okay, thanks.
That's okay, no problem.
Okay, well, no more questions here in the chat or in the list of participants. Okay, well, thanks, Alex. Muchas gracias. Placer tenerte por acá.
Es mi placer.
Muy bien. Pues mañana hay un coloquio extraordinario del director de ASIAN en la colaboración de TESS. Es a las 11:30 Ensenada, 1:30 Seúl. Entonces están invitados también para mañana. Entonces, muchas gracias a todos y por ahí estamos en contacto, Alex.
Sí, nos vemos pronto.
Muchas gracias, Alex.
Gracias, Alex. Nos vemos.
Bravo.